So it's my great pleasure to introduce our keynote speaker, Professor Lixia Zhang from UCLA. Lixia went to join her PhD at MIT in 1981, when really the internet was at its very early nascent stage, and she has been pivotal in its evolution. So for things she's been known for example, the very first IETF meeting in 1986, she was one of the 20-odd participants. This is the standards body of the internet, which was started around 1986, and she's been contributing to it in various different RFCs and standards and so on. She's known, for example, for her work on reservation protocol, RSVP. She coined the term middle box, which is pretty amazing. And now, of course, she's working on name data networking. So some of the things, I think after her PhD, she went to Xerox, the famed Xerox PARC Research Center, and then currently she is the John Postel Chair of Professorship at UCLA. Again, pretty apt there. So for some of the work that she's done in multicast, RSVP, and so on, there are lots of RFCs that you can look up and standards. So she's a fellow of the IEEE and the ACM, and also a recipient of the aptly named Internet Award from IEEE. So without further ado, please join me in welcoming Professor Lixia Zhang for the keynote talk.
Thank you very much. Am I on? Yeah, I think I'm on. I'm very excited to come here, and thanks to the organizers for this great opportunity. This is my first trip to India. Very exciting to learn this great country. So I want to take this opportunity to talk about internet architecture, something I've been working on since 1981, as the professor mentioned, when I first went to MIT for my PhD. The timing was exactly right. As I walked to the MIT campus, my former advisor, David Clark, said that, you know what, the specification for TCP/IP just got published. And here is it. Read it. It's hot off print. That was the September 1981. And since then, I have done nothing but just reading those TCP/IP specifications and see how they actually lit the light and got the whole internet deployed quickly across the globe. Now, why should I take this opportunity to talk about architecture? It's done, isn't it? No, the internet succeeded. I would say exceeded everyone's expectation. So I think I have two reasons to talk about this, and I hope you agree with me. First and foremost, everything. You can look around, everything. It's already got integrated into the internet, or otherwise becoming integrated into internet. Very often, people at this stage talk saying that, what if the internet just turned off for an hour? What happens? We couldn't figure out how life would go on without internet for an hour. So given its importance, are we done with the architecture when we succeeded? I want to use some positive word to say that we're facing challenges. Where come the challenges after this tremendous success? For one, internet continues to grow, still grow rapidly, not only expand to the developing countries and other areas, but also it's penetrating into every corner, even for the developed countries. Like US was the first place where TCP/IP turned on. That actually happened in '83, 2 years after the specification got published. But still, now you go home, you buy some an Apple HomeKit, and you turn it on, so all of a sudden, your home got on internet. So you can watch when I'm here, I could watch what's going on at home. And the second thing is that it's related. There's lots of new applications that are coming online. I'm going to mention some of them we are actually working on. Those new applications really bring in new challenges. They're no longer the old file transfer, otherwise remote login, how many people still do remote login. But that was the main application when I started looking into this. And there's yet another bullet. I don't want to put it here because everyone knows it already. Security. Security. We are facing an increasing amount of threats on the internet. And I don't think I need to say more about that. So with that, I think everyone should care about the architecture. You know, the AI and the machine learning may be the head of a line for the day, right? To make a breakthrough so that something that was totally unthinkable can be done. But you know what? That great machine learning lives on the data as collected by the internet. So if the internet doesn't work, nothing else would work. Now, architecture. I know that for people like me, watching this thing for almost 40 years, you see it start from nothing and gradually growing to a global-wide systems. So you can see it, how things get added up. But for later generations, like new students coming to UCLA, when they ask them, have you learned about the internet? Yes, we did. What did they have learned? We know the TCP slow start congestion control. Or otherwise, we know how the Wi-Fi works. But it's hard for them to see the bigger picture. And this is what I want to talk about. This bigger picture called architecture. Architecture actually is not complicated. It's pretty simple, as I show you here. Oh, it's right here. So it's only basically 3 parts. You may have heard, oh, the 7-layer architecture, otherwise 5-layer. But as a system person, there's really 3 parts. There's the transmission, the layer 2, the protocols runs directly on top of your transmission media, so that you can deliver the network data. On top of that, there are applications that says that here's the data, go deliver from me. So to the architecture, the middle guy, the middle layer is the most important one because that decides how the underlying communication technologies actually get used and what kind of service the applications on top of that can get. And when you ask people, what is the internet architecture? Some people, I would say majority of the new graduate students, they're going to draw blank. Architecture, where have you seen that? This is in that old RFC published in September 1981, as I mentioned, that got handed in, and I've been studying it. Day one, when I look at this, I felt, what a bizarre thing. You know, this odd picture, and in the middle, IP specification, RFC 791, just show you, oh, there are 20 bytes coded this way. So what? But as time went on, I studied more of that. I can recite all the 20 bytes, you know, onward and backward. I started appreciating more. It's a great design. It's not really something dropped from the sky one day, but rather it's actually years of effort that led to this specification. So I put the mark down there. Ben Cerf and Bob Kahn, the 2 great fathers of the internet, they actually published a paper in '74. And it takes 7 years from that first paper to actually finalize the protocol specification. So I have a good friend, Steve Deeren. Some of you may still remember his name, given it's all the old names now. He said, let's draw the picture in a clear way. So that was the first hourglass picture he made when he visited UCLA back in 98 to give a talk. And he pointed out that it's really the narrow waist. That's the most important part. However simple you think it may be, oh, 20 bytes, so what? Because that's a narrow waist, largely contributed to the success of today's internet. It is so simple. That's why very often you get this so what impression. But because it is simple, it can easily get deployed in so many different places for different platforms and also across countries and across the world. Below the IP, you have layer 2 transport. And I want to point to something, maybe that hasn't been emphasized earlier. That is, IP being simple, it also does very simple things. Point-to-point datagram delivery. There are two words that's really important I want you to remember. One is point-to-point data delivery. That is from one address to the next address. This, you think, so what? This delivery from one point to the next point is actually inherited from the network before it. That was the telephone network. Again, the new generations, you probably started with your smartphones and do not know the old days where we had to pick up the wired phone to the dial-ups, and that phone wasn't smart at all. Did nothing but converting your voice into the electrical signals and send it out. When the internet and the IP got derived, it's a great design in that you changed the circuit switch to packet switch. That's a great revolution. Nevertheless, the service model, making 2 points talk to each other, did not change. And the second thing is that IP is a datagram delivery instead of the phone, which said, oh, I'm going to guarantee you whatever the delays or the qualities of your voice. IP at the time, but whoever wants to learn something about the history, I can have lots of stories to tell you because my generation's mostly retired now. And not many people wrote down anything. It's hard to collect all the stories, but in my early days of graduate school, we got lots of heated debate, say this way, with people who at the time running the telephone systems and saying that your IP, you guys have no idea what you are doing. The communication system cannot be built on this so-called best effort. It's really least effort. You drop whenever you want to, and that's not a service. You have to have guarantees. And at the time, there were lots of computations. They try to provide the guaranteed delay. That's difficult, but mostly they guarantee the delivery of your packet from host A to host B. The end result, the market tells, it's the best effort service that eventually win away. So what else can I say? It's very simple, right? But I want to explain to you why this IP designed as a point-to-point communication just inherited from the telephony. Because at the time, the dominant applications was log into remote machines, so you can share some very limited resources. This sounds silly for new generations, but back then, in the old days, there are not that many machines, very few. When I started, I think in my department, I had a big one called the TOPS 20. It's a Honeywell machine. Everyone just had an account. You remote log into that. So this point-to-point communication model served, just did the job. But over time, we no longer do that. People no longer even know about that's how you get the internet started. These days, I listed a few applications that mostly people use on a daily basis. The first few, like the Facebooks, the YouTubes, they've been there for a while. They've been very successful. And they built directly on top of TCP/IP. However, I would add that they also added changes to the original very simple internet. In the original simple internet, you just have a routing protocol to figure out where packet should go, and packet will go there. TCP will recover from losses, and that's it. That's how remote login works, how the file transfer worked. But when you come down to build gigantic data centers, that's no longer adequate. You cannot everyone log into the YouTube gigantic mainframe to think that it can serve 5 million users simultaneously. No, they cannot. So people start building functionalities on top of IP, on top of TCP. They call the application level overlays. And then they said, oh, we're going to do functional virtualization for all the functions that the IP couldn't get delivered. But nevertheless, I should say that things worked out really well. That's how they got used daily by millions of users. But look at the last few examples that I showed you here, like a vehicle-to-vehicle networking. Here, I don't mean to say that my vehicle sends a signal to the next guy to say, hey, avoid collision. That, I don't call it networking. This is just one hop notification. The vehicle-to-vehicle networking people envisioned is really like the vehicles talk to each other create a network. It's not just one hop signaling. And that, if you talk about academic publications, how many years have we been publishing that kind of papers? That's the first question. The second question is, where's the deployment? And if there's no deployment yet, which I think is the case, why? The next big thing has been talking a lot is about the home networking. Think that you got a smart home, you can talk to everything. But again, your home networking isn't home networking. I don't know how many people here tried the iPod, the HomeKit. You order something from Amazon, it arrived. Now, can you just really plug it in so be part of your smart home without bothering anybody else? You cannot. You cannot. If you have tried, you have to have network connection so that up to the iCloud, they would interfere with how you can configure this new gadget into part of your smart home. Now, cloud worked out great, but then again, we should ask the question, how come and why cloud has been so successful? Can we live the rest of our lives just on the cloud and without any doing other things? Can the vehicle-to-vehicle networking get successful by depending on the cloud? Well, by the definition, that doesn't seem to be fit that well. Now, the latest thing I think everyone have heard is virtual reality and augmented reality. Some people may think that's still far away. I think they are coming sooner, maybe, than you expected. UCLA has a big medical school. They are already talking to you about how to get VR and AR to facilitate like the diagnosis of patients, and even more exciting, to apply AR in the surgery. Because humans, they need broader views of things to help. I'm yet to understand how that can help, but definitely that's a great new frontier in terms of networking. They all need networking to hook up things. The question is networking up to the challenge? Can the AR just use the cloud like everything else before it has been done? And that I want to pose as a challenge. I think the challenge really has a cause. All the problem has a cause, right? What we envision AR is really augmented reality. I'm in this room. What I can see with AR is not just what my eye could see, but rather the AR means that this reality my eye can see will be augmented by what? Anything you want. Right? I have a problem with remember anybody's names, but maybe with AR, as I look at you, your name somehow will showing up. That's not far stretched. When I was at home watching the Christmas TV not long ago, not Christmas TV, the basketball games, and I noticed that some audience has a red nose in front. I said, how did they get that red nose in front? And my kids laughed at me. They said, this AR. In the real-time television shows, people already kind of started decorating the reality with augmentation. Those, I doubt, could be handled through that cloud, which may be 1,000 miles away, and to react in real time. So there's a big difference, big problem that this very simple hourglass picture doesn't tell you. That is, the different layers actually do different things. Applications, they don't know IP addresses, and they don't want to know. Applications, if you run a web application, What you have is that you have HTTP request and HTTP reply. You get URL, you get contents. So that's what the application does. Network, on the other hand, that we all know and love, is the IP. IP says everyone get the address and then shoot your packets to it. So there is this fundamental difference, or I would say a mismatch. Now, why would you care this mismatch given the IP has been doing so well? And I tell, here's why. Think about your laptop. You know, I said you run a web application. The application side, here's the HTTP request, get me this piece of data. But IP would say, give me an address, I send packet to that address. How you convert from the first to the second? You requires some kind of translation from the name to the addresses. And I tell you that the translation is not a trivial, just a lookup. Like the old days, you look up your yellow page, oh, there's Mr. Smith, and here's the phone number. The DNS to IP translation goes far beyond that. Just like I said, when you try to fetch the YouTube, not everybody actually talks to the same machine because it has lots of problems. Where you are, where the content is, how many people are trying to look, all the scaling issues. So therefore, DNS service itself is a gigantic, the infrastructure service. And before that, you want to send the IP packet, you have to get the IP address first. So you require the DHCP is deployed infrastructure services to really get you off the ground. Therefore, I think it's a very simple things. You say you have an application, want something, and want to send the IP packet out. Behind the scene, there's complex operations going on. So you really have the dependency on the infrastructure. And also, besides that, we also don't have very great security built into the system as well. When I say the infrastructure, especially when you talk to new students, they don't believe there's any infrastructure needed. And I often use this example to explain to them that you need something before you can actually networking. Say I'm here, I've been mumbling for so long, you want to see what other things Lixia going to say for the rest of the hour. My file is on the slides. I'm just on my laptop, I'm just showing it off. If you, one of you are called Bob, trying to get my slides, can you get it? Assuming that we turn off the DHCP, turn off DNS, get rid of everything else, we can still have Wi-Fi. If no access points, my laptop runs Wi-Fi and your laptop runs Wi-Fi, we can run ad hoc Wi-Fi. The signal-wise, we can reach each other. But I give you my file name. Can you get it under this very simple scenario where nothing exists but ad hoc Wi-Fi? Physically, you should, because signal can reach each other. Just like when I talk, I say, hey, what time is it now? You can answer me, right? My voice goes through the air, there's a communication media, and you understand my question, answer will come back. And since the security people very often talk about Bob, we'll have to mention Alice, so I put the Alice here too. We say that, can Alice also talk to Bob and learn about my file and get a copy of that? Similarly, there are difficulties. Like I said, I can ask you a question, I get the answer back. And our machines can talk through the Wi-Fi just in the same way. But how come they cannot do it? And they are doing. I say that there are two other people, right? If we talk and say, what time is it now? You say it's about 10. And if Zhang and Karen there, they can hear it as well. But that's not how we work today. How we work today, we put the IP in front of whatever data we want to send it out. Now, if I want to, my laptop wants to ask you what time is it now, what IP address do I put as the destination? And similarly, I need an IP address so the answer can come back. And what's that IP address? Besides IP, oh, actually, you know what? My application just doesn't understand IP. So what is the name I have to use to translate into IP? Those now become obstacles. For people who want to do this ad hoc networking, for people who want to do like delay tolerant networking, and many things. So put a long story short, this almost, I would say, more than a decade ago, this gentleman, Van Jacobson, you probably have recognized his name if you have studied ever about the TCP congestion control. But you may not have seen this Google talk he gave in 2006. The basic talks about a new way to look at networking. I think even after 12 years, it's still worth an hour to watch that talk. But if I just summarize the essence of that talk, at basic size, today we do internet through this point-to-point IP packet delivery. That no longer matches the requirements of the new applications, where most of them are based on the web platform. And that consists of the request reply for data. So therefore, a better way to do networking is to really follow that web semantics, but bring it down to network layer. And so that talk and led to a multi-campus collaborative team. We decided to say this is a great vision, we're going to work on that. And then we got funded by the US National Science Foundation back in 2010. We gave it the name, called the Named Data Networking. That just follows to say you request data by name and you get data back. So my machine started running without me. So how does this named data networking works? Like we do architecture, I want to show you what's the big picture. Look at this big picture. It's very, very similar to what IP picture looks like. It's still hourglass because it's a great architectural shape. With that narrow waist, you can have lots of changes below the middle, and you can have lots of new applications on top of the middle. And the two can evolve themselves quickly and independently without interfering with each other. The challenge is really how you design this middle so that they can take the best use of the underlying transmission media to serve the masters, the applications. In the IP design so far, we say that, well, we run our own business. We have our own namespace. We call it addresses. So whatever you do, give me an address, I'll deliver your packets. And this new way of doing networking says that, you know what, we serve the master of application. So therefore, we're just not gonna take your URL from the application and send out a request directly. Equivalent named data means that using that application name to request data, but now it's at the network layer, directly. So that's why I painted application all the way down to the network layer are the same color because they share the same addresses. So although the shape is the same, but you can see already is one big difference. IP user names, and then IP user address, and then user names. And immediate next difference is that IP user address to name host. Actually, if you want to be precise, it name an interface of a host. If you are multi-interfaced, you get multiple addresses per device. And in the end, when we say we use names, we're not naming host. You look at your URL, it's not a host. It names a piece of data, HTTP object. So the name names data instead of a host or host interfaces. And immediately following that, there's another thing, which is that you name an IP packet with an address, network delivers it. If you name a piece of object, UCLA slash Lixia slash web page, my page is going to stay there, going nowhere. So someone has to fetch it. And this change from address to name, address to host to name for data, lead to the third change. That is now, instead of we push the packet out, now this time you have to fetch the data. There's also one big change, but I want to mention in the next slides. But this does 3 major changes. Still, conceptually, it's simple, still hourglass. But the changes really lead to fundamentally different ways. I will show you how this automatic thing can be done. That is, you can send a URL equivalent at the network layer. But I want to show if you can do it by my words, and you can see how the picture gets changed. We removed that mismatch between the application and the networking. We no longer need that gigantic infrastructure just for 2 nodes to talk to each other. Because when I say, request this data, by whatever means the other device get my request, then they can respond. If they don't have the response data, they can go out just carrying that request to say who has this data, and then return back to me. So therefore, it also frees the responders who can send the reply to me. When I send an IP packets out, it has to reach that particular host. But if I'm asking a question, the answer can come back from different computers. As a matter of fact, that's what they're doing today. When you say you look up YouTube, you have no clue which machine actually sends you back the answer. Any of the many the hidden boxes that Google already deployed. Or otherwise, if you ever play the BitTorrent, you want to download some file, right? Exactly who give you individual pieces, you do not know and you do not care. Why you do not care? Because you can verify. Every piece of BitTorrent data chunk, when you get, you can verify. Okay, to do the verification requires, there has to be security checking, the authentication that go with the data. So for the NDN network design, it's just like equivalent to HTTP request response. So we have an interest packet corresponding to request, and there's a data packet corresponding to the response. And you can see there's some differences here. The HTTP reply comes back, it's just HTTP reply. When you heard the name secure HTTP, that's a lie, because HTTP is never secured. The so-called secure HTTP is basically running this HTTP exchange over a encrypted TCP channel. So HTTP itself doesn't really have a security, but in NDN, every piece of data by architecture requirement must be authenticated by the crypto signature. So how it works, whenever the producer produces any piece of data, you sign it right away. This signature will bind the name to the contents. And after that, you don't really care where to get it stored, cached, because receivers can always verify whether the things is right. It's just like your BitTorrent data chunks. So whoever is interested in the data, you throw out your request and get it. Because the data is signed, it can really come from anywhere. You may ask a question from where, other than the producers. That question will be answered later. But I'm going to say just a couple more details. Why is that for HTTP, you actually name a data objects? It could be small, 200 bytes. It could be very large. That's the application layer. You do whatever you want. Now we're designing NDN as a network layer protocol. A network layer has this intrinsic limitation called MTO. If you want to fetch network layer packets by name, you have to name every packet. You name every packet. Well, it's not hard. I give the example of my this presentation. I said, okay, here's my file name. What is that version 20? Because I changed it many times. I put the version number every time I make a change. And then you chop into segments so that each one will fit into one packet. I said 2 very important things here. One is NDN name every packet. That's how you fetch it. At the network layer, you fetch the data packet. And the second thing I said is that NDN use versioning so that data is immutable. Every time you make a change, you effectively produce the new version. And that new version has a new name. So therefore, the name to data binding never changes. And then this thing called obsolete, the concept does not exist for immutable data. You can only talk about which data is produced earlier, which one is produced later. But they do not obsolete in the sense that the name is still there, but the content changes. That doesn't happen with NDN. So now with the NDN, now Bob can easily get the file from me. You send a request, and I came all this way from LA to Los Angeles, from Los Angeles to India. I want to tell you how NDN works. So I'm more than happy to send you back the reply. So you can see here that you just send a request, and data will come back. And in this data packet, what I want to point out is how does my machine understand this discover request? That's by naming conventions. Say there's a well-defined keyword. When my machine receives that request, it knows how to interpret. Interpret by saying, oh, it requests for any publicly available data. And therefore, I'm going to send back the information that matches that request. How I say the matches, if I have a pointer, because there's a prefix that matches the request prefix. And under that prefix, I will supply any names that I'm willing to share. And in this reply, this will be the NDN interest packet, and this will be NDN data packet. And in the data packet, I will supply you additional information about the file, like how many packets in it. And therefore, I'm not used to this, so that if Bob is interested in fetching it, you can fetch it. One interest for one data packet. And if you want to fetch quick, you can pipeline in the interest that we know all about how we do that. There's additional questions that people may have when I gave this talk earlier to say, what if in this room so many people want to share information? Are you going to have to send the discover many, many times? I use this example just to give you an illustration how the concept works. If you talk about many people sharing information in the local environment, we actually use a different concept called data synchronization, where when you send discover, actually I'm going to tell you, okay, here's all the available data you can get. That will include not just mine, but the other data that I have heard. The data set synchronization is a very exciting topic. It is so useful in distributed applications, but I won't be able to say details. You can look at some of the literatures we have produced. Now let's bring Alice into the picture. So, okay, Alice wants to get the file. So even before Bob has asked. Now, what happens next? Assuming this is a really collaborative local environment, Bob always helps Alice anyway, so that Bob will be able to forward the request to say, hey, what's information available in this room? And then get the response and send back to Alice. But exactly how this happens, if I'm not turning Bob into a HTTP proxy, we're talking still, remember, we're talking about the network layer. Network layer, just understand the names and then deliver it accordingly. So NDN really want to build this kind of a data dissemination environment where the concept of nodes disappears. All we have is that someone requests for data, and whichever way the data exists, the network will do this automatic thing. We'll get the data in the best way possible to the requester. So I just show you some details to say that it's not auto magic. This actually has been implemented in the NDN code base. For all of these machines running NDN, they essentially have this module called NDN forwarding daemon, or NFD. How is the NDN forwarding daemon different from the IP module? First, it has a table that the IP doesn't. It's called a pending interest table. If you want to receive interest and send data back, you keep that pending interest table. This table works not just when you help other people to fetch data. It works even for yourself. And then treat all the interfaces to the network, and also the faces to the application. We now all call the faces. So the NFD basically is a big switch. You can think that way. Okay, all these faces, application, my local application can send request out that will put a entry into the pending interest table. Or otherwise, if I receive an interest, I want to help forward, I put the entry in the forwarding interest table. Now, once you put the received interest there, then you figure out, okay, am I going to send it out? And which way to send it out? Maybe you have the data locally. You can just reply. When my NFD receives the packet, it actually look up the application who registered for that prefix, it will send to that way. But in Bob's case, it's going to make a decision to say, I will help forward this interest. Who makes the decision? There's another module in the NFD called forwarding strategy. And this is also something that the IP box doesn't have. Because in the NDM module, there are decisions to be made. So therefore, forwarding strategy is there to make intelligent decisions. I'm going to say more about the forwarding strategy later, but let's move on with our story. So now that Bob can relay the request and get the reply back and forward, because you can see that the pending interest table has the outgoing interface. When data comes back, they can just traverse that path that's already set up and get the data back. So in both interest and data packet, there's no address. Nowhere has this concept of so-called nodes. And yet, interest packet can be forwarded. Now I do this kind of a learning discovery. And later, I'm going to tell you that interest packet can also be forwarded globally if you run a routing protocol, so that Bob will know which of its interfaces is the best way to reach the requested data. Another thing I want to say is that, so the data packet will get back to the Alice. And what happens with the Bob? When the data packet gets to the Bob, what the next thing Bob can do besides just forwarding to Alice? There is something that's different. This reply I sent to Bob has nothing to do, well, it got there because Alice requested, but this packet itself has no indication this is actually for Alice only. In the packet, there's data, there's content, there's signature. So therefore, this packet can be thrown to anybody who wants to do discovery of the information in that given local context. Packets, data packets, is independent from requesters. So therefore, it can stand on its own. As such, in that NFD, there's a third module there. It's called the content store. So therefore, the content store can cache any data that has been received. Just in case someone else asks for the question, I look at my content store, oh, I have the answer, I can get you right away. Not only you can help with giving the answer to other people who asked, but also think about this way, that what if the packet get lost? The wireless is so good, but not perfectly reliable. When packet get lost, NDN learn from IP. We still do datagrams. There's no guarantee at the NDN layer to say, okay, we'll guarantee deliver you. But the Alice ask the question, never get answer back, you're going to retransmit. This is equivalent to that TCP, you don't get an ACK, you're going to retransmit. But what happens, different from TCP, is that TCP's retransmission has to be end-to-end, because nobody in the middle knows what's happening, right? IP is stateless, as we were told. In NDN, on the other hand, the name identifies the data piece. And the data piece can come from anywhere, as long as a matching piece gets founded. So therefore, the recovery will go hop by hop. We're going to hit right at the nodes where the loss happened in the next step. So that fundamentally changes how well the network can behave in a lossy environment. Some people run simulations and was amazed to see how come your NDN behaved so well because of this cache. So the next thing is about delay tolerance. See that Alice got the whole file. What she's going to do is she carries the file, go on the bus. And on the bus, she might, there are other people doing discoveries, and she might share the file. And I would be very happy for lots of people to look at this stuff. Right? So what we just have said is actually something called the delay tolerant networking. Right? You carry the file, become data mule, you carry to other places, and share with them. In today's IP, I think delay tolerant networking was, or has been some big research area for some long time. And where is delay tolerant networking today? After, I don't know how many papers get published. Where is it today? It's not that people don't have good solutions. It's just extremely difficult to have that actually built into the system. But look here, what do we have done? We haven't done anything different, but rather just the inherent design of NDN can accommodate delay tolerant networking. Because all is needed is just to say that you can carry data, and data is independent from the carrier, and the data can be verified. So therefore, anyone who can get it. On the bus, if Alice wants to share with people about the file, which is about 10 megabytes, so the best thing is you use this near-field communication. Now, among the phone's many interfaces, which way is the best way to use? Now, like I said earlier, there are many decisions the phone can make, and the forwarding strategy will be the one to help make this decision. I'll tell you how that's going to happen later. But the fundamental point this slide wants to show is host multi-homing has been quite challenging in internet because the IP address is associated with each interface. So, and your packet only goes to one interface, and you have to figure out a prior which interface you should use. And that's how things get difficult. But here, because you don't care about the interface, the forwarding strategy will figure out, oh, I have 4 options, which one to go? Then you can make the option, the decision based on that. Now let's go quickly to see exactly how this automatic NFT actually works, even in a larger scale, say in the global scale. We actually have an NDN testbed, if people don't know, that runs across 4 continents. 4 continents is pretty long. So besides the 3 things we mentioned before, the forwarding strategy, content store, and pending interest table, you can see necessarily we need something that's IP used today. It's a forwarding information base. That's where you're listed, okay, for this prefix, now we use name prefix. Which way should it go? How you learn about that? In the early example I showed you, you can learn from self-learning. Try that out and see which one it works. Otherwise, you can learn from routing table. So this FAPE has 2 differences from the FAPE in the IP router. For one is this name prefix instead of IP prefix. But for 2, that's even more important, is that for next hop, you can list many. In today's IP router, how many next hop per prefix? 1. Why you don't list the 3? It's not because you don't have 3 alternative paths. I tell you, before NDN, I studied the routing. There's so many redundant paths these days because the network is so richly meshed up. But in routing, we can only put a 1 next hop because we are so worried about loops. Even with a single path forwarding, we still have loops. How come we don't care about loops here? Because remember, every time you forward an interest, you actually keep a copy in the forwarding pending interest table. So therefore, if any interest ever looped back, you know it, and you can kill the loop. This really frees you up to try all the alternative paths and see which one works better. So the data producers instead of today, like UCLA inject 8 prefixes into global routing table. And in the NDN, UCLA just inject UCLA.edu into the global routing table. Now, you may ask the question, I've been asked many times, how would this scale? Okay, UCLA can inject it. What about me? I registered, like my son registered a name, fullbars.com. If everyone registers a name and inject into routing table, how does it scale? I won't be able to answer that question, but I can point you to some of the published paper talking about that problem, how we actually can solve that problem very effectively. Let's move on to give you an overview of how exactly an interest is going to walk through this NFD and find the best way to bring data back. When the interest comes in, you see, do I have the cache? If you so, then data already go back. Otherwise, you ask a question to say, hey, I'm talking about this table is mine. Have I seen this request before? If so, I don't have to send it again. I just have to remember which interface the request actually comes in, so that when data comes, I will send back a copy to each of the interfaces I received the request. Then if you do not have a PIT hit, then you have to look up a FIB. Where do I forward, right? You have many options. You can also drop it. So the decision will be made by the forwarding strategy. Not only you may forward along one interface, you can forward along multiple interfaces and just see which one can work better. How do you know which one works better? Because data will come back, and that you will know. Data comes back, you ask the question, did I ask for data? If you didn't, that is, you cannot find the matching entry in your PIT, you drop the data to avoid anyone DDoS you by the gigantic data packets. If you can find the match entry in the PIT, now you have measurement. How long does it take? You can estimate the throughput. Do whatever things you want, because it's a closed feedback loop from the interest to data packet come back. You use that for your congestion control, for your load balancing. Oh, this way goes slower, that way goes faster. The throughput is different. How am I going to adjust my future interest forwarding? Then you can send data back now to whoever asked for that. And then you put into your content store. Then you can remove the PIT entry now. The job has been done. How many things I have talked so far? You can mitigate DDoS. You can do measurement. You can do multicast delivery. And you can do caching. Those things that we all wanted to know. We wanted to have, for the internet for many years now. Now, we only have this one simple pending interest table. It achieves all. So now I want to say a few things about forwarding strategy. In today's internet, the routing plane, now we call it control plane now. You know why? It's because the routing controls. The forwarding knows nothing. You just shoot the packets out based on what the FIB says. But in the end, it entirely changed the relation. Because who is the boss now? The forwarding plane. The routing plane, well, basically, it provides the input to say, oh, if you want to forward this way, you may consider going. You may consider going, because the consideration is by the forwarding strategy. It takes the input from the FIB to say, oh, you give me 3 options. Then what I'm going to do is I would consult my policies, what my policy says. Will this interest be forwarded, be dropped, be split? And the more importantly, I have measurement data. For the same prefixes, I would try this and try that, which way is better. Then you can make a decision accordingly. And people mentioned about the energies, right? Now, in my policy, I can take into account how much energy I have. Should I forward? So I heard the comments from other people to say, this sounds pretty complicated. At least a lot more complicated than IP routers. Is it so? Let's look at this. Yes, we added the content store. But you can see how much the content store actually help the network to bring back the data the user wanted. That's the whole purpose for the network to exist in the first place, right? You can really speed up the delivery and reduce the network load. That is, you have a cake and you can eat it too. So therefore, that's justified for this existence. For the PIT, you have multicast built in. Multicast always required state. That's from day one when that was designed. And you have the feedback loop so that you can do all of these things everyone wants to do for many years. The difference is that today we do congestion in one way, we do load balancing in a different way, and the measurement, and yet some other means to track it. Here we have one PIT. It does all. The reason is because PIT stores state, but it's a per packet, per hop state. It's the finest granularity of the unit the network actually handles. If you have that state, it really allows you to get all the information you needed for your actions. And people also talk about DDoS. We have papers developed. We're going to just skip that. And last, I want to mention something a little more philosophical. People say it's too complicated. We want to save. Look at your user, the name, how long it is. IPv4 only have 4-byte address. Your name, definitely longer than 4 bytes. What's the answer to that? My answer is always that, look at the IP routers. It's way more complex than the telephony switches. Now, where is that more simpler telephony switch today? It's get replaced by the more complicated IP routers. Why? Because the technology moves forward. You cannot say, now I take 4 bytes, do the business, so I always take 4 bytes. It's always a better solution than the other things that are going to take 40. That's not the answer. The technology moves forward is for you to use that technology to better serve the users. And you cannot use the same absolute number to judge whether you are moving to a better technology or otherwise. So we have that paper that gives detailed discussion. Now, I'm trying to say something about the NDN. NDN can do many magic, but fundamentally, it's a name. That's why we change the name. We will use the name the data networking. It's the same name. You can use for multiple interfaces. You can have automatic the information discovery just throughout your request and see who has it for it. And you can support ad hoc delay tolerant networking and the same name used across all the layers. Many years, people have been talking about cross-layer optimization. Now you got it. You know exactly what the upper layer is asking for, so the lower layer knows how to handle it. The next thing is about security. How is naming data really help the security? Because now the data has a name, you sign it, so that you secure the data directly. You can also encapsulate that as we have done. The most important thing is that security is not about crypto. Security is about the key management. Which keys can send which data? And how you verify the keys. Those are the hard questions. So those are standard things, authentication, confidentiality, and availability, that's all the same, whether IP or NDN. What NDN makes a difference is that you can do this automatically. For support redundancy, for availability, we have talked a lot, so I'm going to focus on how we can handle the crypto keys in an automatic way. I'm a little late, so I'm going to go very quickly. Some details. I didn't mention earlier, that is, in the crypto signature, it has a pointer to the signing key. It's basically just a name. And with that name, you can fetch the key. For now, you say, I received the package signed by UCLA. Fine. What is UCLA's key? How do I get it? That's another big question out there. For NDN, everything is a piece of name the data. You want to know something, give me the name, network fetch for it. The interest can also be secured as needed, but we'll skip that. So how you can use the crypto in the NDN? Basically, you do sending, you do verification. There's the standard things to do the encryption. what the NDN differs is we use the names, and name the data can carry the security policies, can carry the keys that make things easier. So I think instead of going through this one by one, let me just give you some pointers so that people can persuade later on their own things. So essentially, let me go up this one. Essentially, you send things and you need to do verifications. So NDN what I give you is that once you define your policy, all this key management, which key sending what data, and who can decrypt your data, these things can be all built into the library automatically. And those are the references. This thing I really want to say because I got asked many times to say you violate end-to-end principle, left and right. You get data from anywhere. Yes, but that's the only way you can scale. If everyone pound on the same server, it will melt quickly. Today, you really don't talk to that same server anymore. So the end-to-end has to be considered in a new light. Because you don't talk to the same server, so the so-called end-to-end no longer, well, by and large, exists today. When you talk to your bank, your HTTPS request, where does it end? You think it's your bank server. I don't know about in India, but in US, I have actually looked. It doesn't end up in your bank server. It's end up in the middle box. And the middle box, run by others, not your bank, do security check. So you already lost the so-called end-to-end security today. Now, what the NDN does is that, we understand that you may not be able to directly talk to the other end you want to talk to. At least we make sure that the data you get is produced by the other end that you wanted to get data from. So that's actually the true end-to-end security in today's environment, where you have to scale, you don't talk to the same server, and also you have intermittent connectivity, then you don't have the chance to talk to the end, if two ends are not online at the same time. So to summarize, NDN is really three simple ideas: name data, secure data, and stateful forwarding. With the different combinations of those three things, you can get lots of benefit, like I already mentioned. You can cache data now because the data can be verified, doesn't matter where it comes. You can do multicast now because it's stateful forwarding, and you name the data. And this stateful forwarding provides you all these advantages. And I want to really point it out that you do the measurement that help you make the better decisions for the future. For the attacks, you can inject the bad data into the system. Signature will help detect and verify and get around the problems. You cannot kill the bad guy in real time. You can get around it. So these three things provide you this really resilient data delivery. Let me just say, with all of that, where we are getting to. So what we are getting to is that network. Network does one thing, delivers your data. Network runs the routing protocol. It knows exactly which best way to get your data. But today, when we do like peer-to-peer file sharing, where is that sharing? It's an application layer. And you lost the touch with the network. You don't know who is nearest to you. You don't know whether you actually cross your ISP boundary and make them unhappy when you download the 10 gigabytes of files. If you do all of this content fetching at the network layer, that actually solves the problem. It combines the network power, knowing what things where and which way to go, with the semantic understanding of exactly what you want to get. And that's where all this power comes from. So the fundamental question of networking is that what namespace you use. In NDN, we say which you use, whatever applications use. And that will enable you do the same thing, like ask a question. Your machines can also talk to each other directly without any intermediate translators. So this will enable infrastructure-free applications I don't mean to say infrastructure is not good, cloud is not good. It's great, but don't depend on it. When the Amazon had a glitch, I still want to open my door. I don't want to be just shut outside. And to close up, I want to say that once you can request data by semantic meaningful names at the network layer, you actually can integrate not only networking, but the storage and the processing. Why? Because you can express what you want. For 7 years of doing NDN research, one thing we appreciate the most is the expressive power of that name. You can ask for the things that doesn't exist yet. I ask, we're now let me just go. So these days, we're doing this joint project funded by NSF and Intel. The requirement is very simple. Run the latest application over NDN over wireless. Where's the IP? We don't need the IP. Especially at the edge, you can run anything you want. How do you do it? Because NDN talks semantic names at the network layer. Like this really literally sensing the environment along my hallway. Well, my old hallway, I just moved office. You can see that you pull off your phone talks to your environment, and you gather the data you want. So without any translation, without any infrastructure, this is purely over Wi-Fi, Bluetooth. It's about, okay, I'm here. You cannot see clearly. This is actually Professor Cranrock, one of another internet fathers. And it tells you that down that hallway, there's a talk going on given by Alex. That's only simple sensing. The more advanced things is that not only we can sensing the net environment, we can request the services. We built some prototype to say my phone actually recording the video, and the video will be processed by some machine learning to do the object identification and then face recognition so that you can really add the semantics to say what's going on. And with that, then you can request related information. Oh, this is a design meeting, and it will automatically supply you with additional things. So here you can see that this is a many-to-many communication. When you say you want your video to be analyzed, which server do you talk to? Which server do you talk to? Well, in NDN, how does a server get a request in? Let other people know what you are. You say, I do machine learning. So therefore, my request with the machine learning as a part of their name will get sucked into that machine learning server. And the result will come back to me. With that, you really blended processing, networking, and storage into one named semantic network. So, so to the end, I just want to remember, this is where we started by talking about internet architecture. Very simple, 3 pieces. The middle one being most important. So I think the future of the internet really relies on recognize the right abstraction model for that network layer. And we started hundreds of years back. We have the telephone. The network layer model is a circuit. And then we moved to IP, the network layer model. It's a packet switching, but still a virtual circuit between 2 ends. It's a great virtual circuit, but nevertheless, it's a circuit. And the NDN size, we now really need to move the semantics of the network service to become requesting for named data. So over 7 years, we have built quite a lot of things that run in code base. It runs not only in the local environment, we also build a test bed. This is our website. You should take a look. And I want to tell you there is still so many great challenges ahead of us, and I hope people will become interested to look into that. You can help. Thank you very much.
Thank you. Thank you very much, ma'am, for that very interesting talk and a glimpse into the future of the internet. In the interest of time, I think we'll only have a couple of questions. Sir?
Thanks for the interesting talk. what I have understood from the talk, if you are addressing the host, if that has to be changed to address the entire URL by name, because that's what is name data networking, where you are addressing the entire URL by the name. Then if the name has to be addressed, you have a single URL. Will that not be a huge task? Because you are replacing the entire URL by the name. So will it not be a very complex task?
I think maybe you meant to say the name will be long as opposed to complex.
Because you are searching with single name.
You see, when you send the IPv6 packet out, the destination is 16 bytes. It's pretty long. The router doesn't really look at 16 bytes per se. They look at the prefix. The same thing for the forwarding of the names.
Will it not be a huge search space for name?
You do the longest match, just like what we do today with IP table lookup.
Okay, thank you. And one more, will this still be connected with the internet? Can this be run through the internet, existing internet?
If I ask back, did the internet interact with the telephony network? I think people who has a memory could answer that question.
I have two questions. So how does this performance compare with other ad hoc routing protocols like AODB, DSDB and things? This is one question. And the other question is, have you compared the performance with internet routing and the performance in terms of delay, throughput, RTT? So how does that compare?
I don't think I heard your first question very clearly. For the second question.
Okay, so I understand that this is an ad hoc routing kind of scenario. So there are some ad hoc routing protocols in the literature before run, like AODB, ad hoc on-demand routing, DSR, dynamic source routing.
For the sake of time, I didn't get into ad hoc routing. I want to say one thing. It's really the insight. Today in IP, when your computers come together ad hoc, you have to run a routing protocol. Why? Because otherwise, how do you know which computer is where? You have no clue. You send packet out. You don't know whether it succeeded or failed. In NDN, in small scale, you do not need a routing per se. You do the discovery, and when data comes back, you already found the successful path. Because the forwarding is stateful. That really replaces routing. What is routing?